Hello math friends, this is AP Calculus section 1.5. Today we're going to be talking about exponential functions. Recall that an exponential function is exponential because the variable is the exponent and the base is some positive constant. Now if our base is a number that is between 0 and 1, that's when we have exponential decay, which looks like it is decreasing from left to right. If a were to be 1, this would actually be just a constant, like y equals 2, because 2 to the first power is 2, which just makes a horizontal line. So we don't really consider that to be exponential at all. But technically, if you think of it as exponential, it would just be a constant function. And then if our a value, our base, is greater than 1, that is when we have exponential growth. And of course, a couple features to keep in mind. Remember that on all of these graphs, we have that horizontal asymptote here at y equals 0, which is always there, and it does move if we have some sort of a vertical shift of our exponential function. But for any parent function, we're always going to have a horizontal asymptote at y equals 0, meaning our curve either lives above it or below it, but does not cross that line. Let's take a look at our first examples. In example 1, they want us to use parent graphs and then the transformations on those parent graphs to graph the following exponential curves. So let's take a look first at letter A. Our parent graph for letter A would be the function y equals 2 to the x. Now, based on the fact that my base is 2, which is a number greater than 1, I know that this is going to be exponential growth. So I can go ahead and I can sketch what the parent curve looks like for y equals 2 to the x. So I just start plugging x values in, and I just like to do my fave 5, x equals -2 to +2. When x is -2, 2 to the -2 power is really like 1 over 2 squared, which is 1/4. 2 to the -1 power is 1 over 2 to the first, or 1/2. 2 to the 0 power, anything to the 0 power is 1, so 0, 1. 2 to the first power is 2, so 1, 2, and then if x is 2, 2 squared would be 4. So you can see here my parent graph for y equals 2 to the x. And again, don't forget, I do have that horizontal asymptote here at y equals 0. So then they ask us to use that parent graph to create the graph for y equals -2 to the -x. So we have to figure out what those negative signs are doing to our curve. Hopefully you remember from an earlier lesson our transformations, and these two are both reflections. So this negative out in front of our base, that is going to be an x-axis reflection. And this negative sign up here in the exponent along with our variable x means that we are going to reflect over our y-axis. So we're just going to take each of these points and we're going to reflect over the x-axis, reflect over the y-axis. So I'm going to start on the left and work my way to the right. That first point, which right now is at -2 1/4, is going to be at +2 -1/4. The second point, which is at -1 1/2, is going to be at +1 -1/2. The point at 0 1 is going to be at 0 -1. The point at 1 2 is going to be at -1 -2, and the point at 2 4 is going to be at -2 -4. All right, I didn't have any shifts, I just had reflections on letter A. Now let's take a look at letter B, and again, we will start first by graphing the parent function. All right, and my parent graph here is y equals 3 to the x, which again, because my base 3 is a number greater than 1, this represents growth. It is going to grow faster than letter A, which was 2 to the x, because the base is bigger. The bigger the base, the faster the exponential curve climbs. So I do the same thing. I start plugging in x values. When x is negative 2, y would be 1/9. When x is negative 1, y would be 1/3. When x is 0, y would be 1. When x is 1, y would be 3. And when x is 2, y would be 9. 3 squared is 9. So here's my parent graph for letter B. Again, my horizontal asymptote is right here at y equals 0. All right, so now I take a look at the function that they actually want me to graph, which is y equals 3 to the x plus 1 power minus 2. So it looks like I have two shifts going on. Remember, your horizontal or left-right shifts always happen where the variable is, and then your vertical, your up-down shifts, always happen after the function. So I know that this minus 2 is going to be a vertical shift down 2. And I know that this x plus 1 up here in the exponent means that I am going to have a horizontal shift. Be careful. Remember, the horizontal shifts are always opposite of what you expect. So if it says x plus 1, this is actually going to be shifted left 1. All right, so I just move each of my points, left 1 and down 2. So left 1, down 2, left 1, down 2, left 1, down 2. Right there. And you might want to note for this graph that because we had a vertical shift, whoops, I have to change that to yellow. Because we had a vertical shift, our horizontal asymptote has now moved down. Right? Our horizontal asymptote is now at y equals negative 2 because that always coincides with our vertical shift of negative 2. For example 2, we're just going to practice our transformations in written form. It says, starting with the graph of y equals e to the x, write the equation of the graph that results from shifting 2 units downward. So if we're shifting 2 units down, vertical shifts happen after, so it'll be y equals e to the x minus 2. Shifting 2 units to the right, that's going to happen up in the exponent. So that's going to be y equals e to the, now if we're shifting to the right, it's going to be x minus 2. Reflecting about the x-axis. X-axis reflections happen in front of the function. So y equals negative e to the x. Reflecting about the y-axis, that happens up in the exponent, so e to the negative x. And then finally, reflecting about both axes, we did one of these. This is negative e to the negative x. So those were easy. Moving on, example 3 says use a system of equations to find the exponential function for the given graph. So they've given us the form of the exponential equation that we are expected to find. They've also given us this graph. Sorry about that. They've also given us this graph here, and they've called attention to 2 ordered pairs that are on my curve. That's the only information that I need to do this. You may remember these problems from Algebra 2 and from Pre-Calc. This is just a system of 2 equations and 2 unknowns. I like to think of it as a 5-step process. All right, so step 1 is going to be to write 2 equations. Given the 2 ordered pairs, negative 1, 3, and 1, 4/3. Okay, so my 2 equations then, I'm just going to be plugging in negative 1 for x and 3 for y into the formula that they gave me, the f of x equals c times a to the x. Remember, f of x is the same as y. So my first equation is going to be 3 equals c times a to the negative 1. My second equation comes from the second ordered pair. That's going to be 4/3 equals c times a to the first. Okay? Step 2 is going to be solve one equation for c. Pick the one you like, pick the easier one. So this is just algebra, okay? So I'm going to start with 3 equals c to the a minus 1, which a to the negative 1 power is actually a on the bottom, right? So this is really 3 equals c over a. So if I want to solve for c, I'm just going to multiply both sides of the equation by a. And so I get 3a equals c. Then step 3, excuse me, is going to be to substitute that value for c into the second equation. Okay, so I'm going to take this right here. Let me switch colors. Oops. I am going to take this right here, and I am going to substitute it in for c right there. That's what I'm doing in step 3. So when I do that, I get 4/3 equals, for c I'm going to plug in 3a times a to the first. And then I'm going to simplify that. 3a times a, and sorry, step 4 here. Simplify and solve for a. Okay, so when I do that, I get 4/3 equals 3a times a is a squared. If I'm trying to solve for a, I'm going to divide both sides by 3. When I divide both sides by 3, I am multiplying 3 times 3 in the denominator below the 4. So that's going to become a squared equals 4/9. And then when I square root both sides, I get a equals the square root of 4/9, which is 2/3. So I just found a equals 2/3. All right, and then my last step here, step 5, is going to be use a to find c. So now I do a substitution again. Now I'm going to take a, and I'm going to plug what I found for a back in, and I'm going to solve for c. So I know that c from right here was equal to 3a. So now I'm going to take my a, which is 2/3. So c is equal to 3 times 2/3. Well, 3 times 2/3 is just 2. So I get c equals 2. So now I'm almost there. Last step is I just have to write the exponential function. I've got my c, I've got my a. I just have to put them together. So my final answer here is going to be y equals c, which is 2, times a, which is 2/3, and I'm going to put that in parentheses just because it's a fraction, to the x power. So that is my solution, or my exponential function that matches that curve. Example 4 asks us to graph the functions f of x equals 2 to the x. We actually already graphed that in example 1. And g of x equals x squared. So 2 to the x is an exponential function. X squared is a power function. And the question is, which graph increases faster, and what are the points of intersection of these two curves? Well, I know what these look like. I already graphed 2 to the x, as I said, and I know what x squared looks like. X squared is just a standard parabola with a vertex at 0, 0. So if I think about what these two curves are going to look like, here's my coordinate plane. And I know that my 2 to the x looks like this. And I know that my x squared looks like this, right? But the question, and I know, obviously, I can see it in my picture, I know that these two graphs are going to intersect here and here. And the calculator, again, will help me with this. But then the question is, how many intersections are there? And that is going to help us answer the final question, which is which graph increases faster. Because if you look at my picture right now, if you look at the picture that I drew, you can kind of see where I guess we'll call it the pink curve, right now is lying on the inside of the exponential curve, right? And so it looks like that pink curve is increasing faster at this point. But the question is, do they cross again out here at some point? Does that exponential curve overtake our power curve or our quadratic function and start to increase faster at some later time? So I know for sure that there are two intersections, but there could be three. So the question is, are there two or are there three? And this is where we have to be wise in using our calculator and make sure that we look at a big enough viewing window so that we can see all of our intersections. All right, so let's go to our graphing calculators. And we're going to put in our two functions, which are y equals 2 to the x. Okay, so 2 caret x. And then my second function is going to be x squared. And I'm going to just start with a zoom 6 like I always do. And there we go. Okay, that's kind of the picture that I have on my paper right now. You can see that there's going to be an intersection right here. You can see that there's going to be another intersection right here. But if you look over here, and you can imagine that this blue graph is going to be shooting up, and this red graph is going to keep widening, you kind of expect that there's probably a third intersection. So we should play with our window a little bit and see if we can see a third intersection. My first two intersections happen here somewhere between x equals 0 and x equals -1. My second intersection looks like it happens when x is 2. So, you know, I'm not sure how big we need to get, but I have a feeling that that intersection is happening somewhere out here. So I am going to change my x minimum to -5 because I know that there are no intersections on the left side of -5. I'm going to leave my x maximum at 10. I think that if there's a third intersection, it's going to happen before 10. And my y minimum and y maximum, well, I obviously need to make my y maximum bigger than 10. I can probably just go -1 on my y minimum, though, because all of these intersections are happening above y equals 0. So let's change my y maximum to, I don't know, maybe 15, 20? Not sure. Let's go 20, just to make sure we are big enough to see. So let's try 20. And we graph. Oh, and look at that. There is a third intersection right there, okay? So you can see that these graphs actually intersect 3 times. And ultimately, the blue graph, which if we go back to y equals, the blue graph is our 2 to the x, is our exponential function. Ultimately, the exponential function is going to increase at a faster rate than the power function. And FYI, that is always going to be true. Exponential functions will always ultimately increase at a faster rate than power functions will. Let's have the calculator do the work for us and calculate the intersection points. So I'm going to go to second level, calculate. Number 5 is intersect, so 5. And I'm going to have to move the cursor around now because there are 3 intersection points. So I'm going to start with this intersection point right here. So I'm going to use the left and right arrows to move the cursor closer to the intersection so that the calculator knows which intersection I'm trying to find. Okay, so I want to get as close to it as I can here. So I pushed it a few too many times. Okay, so it's asking me, is the blue curve the first curve? Yes, I hit enter. Is the red curve the second curve? Yes, I hit enter. Do we want to make a guess? Yes, we do. And so there is that first intersection, which is at negative 0.77 or 767, 0.588. Okay, so I can go ahead and, if I'd like to, I can record that here on my graph, or excuse me, or I can, at least on my, I can write it on my paper here. So my intersection points, the first one was at negative 0.767, comma, 0.588, okay? Then let's take a look at the next one. So we'll go back to our calculator. Now we need to do a second level calculate, intersect again. We're going to bring the cursor closer to the second intersection, because otherwise it's just going to give us the exact same one that we already did. So we need to be closer to a different one here. All right, so now first curve, yep, hit enter. Second curve, hit enter, and guess? There's our second intersection, a very nice one. Our second intersection is at the ordered pair 2, 4. And you probably could have figured out that those two functions share that ordered pair, right? 2 squared is 4, and 2 squared is 4. When x is 2, both of those functions equal 4. All right, and then on to our third intersection. I am going to do second level, calculate, intersect one more time. I'm going to bring my cursor closer to that third intersection, just somewhere up here. Oops, a little too far, sorry. Back up, okay. First curve, yes. Second curve, yes, yes, yes. And the the third intersection is at 4:16. All right, so let's go back to our notes and let's record that intersection. I recorded the 2, 4, and I'm going to record the 4:16 as my third intersection. Okay, and so I want to make a little note right here by 4:16, because there is that point up here where they intersect again, right? And 4:16, this is the point where the exponential curve, which is y equals 2 to the x, increases faster than the power curve, which is y equals x squared. Okay? And the important thing to think about is, if you did not adjust your viewing rectangle to be big enough, you may have missed one of your intersections. Okay, so there's a bear trap right there. The window that we used, let's write it down just for future reference. The window that we used was -5 by 0, or actually we did -1, didn't we? -1, 20. And something to think about, if we didn't make our viewing rectangle big enough, we may have missed an intersection. Okay, so always be mindful of that when you're using your graphing calculator to determine intersections of two functions. Make sure that you are looking at a big enough picture and finding all of them. Our final example here, example 5, it says a certain bacterial culture starts with 500 bacteria and doubles in size every half hour. How many bacteria are there after 3 hours? After t hours, some generic number of time, or after 40 minutes? So we should do some algebra first. Then it says graph the function and use your calculator to estimate the time for the population to reach, this should say 100,000, that should be a comma, check your estimation by solving algebraically. All right, let's back up a step here, and let's think about what our population growth model looks like. And again, this should be review from Algebra 2 and from pre-calc. So our population growth model looks something like this. It's okay if you don't remember it. I'm telling you right now what it is. P of t is equal to P naught times n to the, and it's t divided by t naught power. And I'm going to tell you what all of those things mean, don't worry. So this P naught in front right here, this is your initial amount, like the starting population, whatever it might be, people, bacteria, whatever. The n is how the population is changing. Meaning, does it double, does it triple, etc. And then t is time, t naught is how long it takes the population to change. Okay, so let's put this together in an equation for this particular situation. The population at any given time t is going to be equal to the initial population, which we were told starts with 500 bacteria. So that's my P naught, right? 500. And it says doubles in size. That's my n, right? It's doubling, so times 2. Every half hour, okay? So 0.5 hours, that's going to be my T naught, okay, every half hour. So 2 to the T divided by 0.5. So then I just do a little algebra here, all right? So then P of T is going to be equal to 500 times 2 to the T divided by 1/2 is the same as T times 2. So T over 0.5 is the same as 2T. I can simplify my exponent a little bit. Really, 2 to the 2 times T, I could think of that as a power to a power, like this. This is really like 500, and you'll see this again throughout the year. And then 2 squared to the T, right? Because I'm just doing the power of a power rule in reverse. Usually when we have a power of a power, we multiply our exponents. This time I'm pulling them apart so that I can simplify 2 squared as 4. So P of T is equal to 500 times 4 to the T power. All right, so this is part of our answer, actually. So now let's go through and let's answer all of our questions, and I'll explain what I mean. So after 3 hours, we just have to use our formula, and P of 3 would be equal to 500 times 4 to the 3rd power, and you just grab your calculator. This is 32,000 bacteria. After T hours, this is the equation that we worked to create. So this is P of T equals 500 times 4 to the T. After 40 minutes, that one we have to be careful, because remember, 40 minutes, that is 2/3 of an hour. So this would be finding P of 2/3, which is 500 times 4 to the 2/3 power. Again, you grab your calculator, you type it in. This is not a whole number, so we round to the nearest bacteria. We end up with 1,260. And then we come to the last part of the question, which asks us to estimate, using our calculator, estimate the time for the population to reach 100,000, and then check our estimation by solving algebraically. Okay, so I am going to sketch a little graph here so we can talk about what it is we're looking for. I know that I have exponential growth. This doesn't need to be perfect, but I know what exponential growth looks like, right? It looks like something like this. And I know that my initial, or my curve here is y equals 500 times 4 to the x power. If I want to know when my population reaches 100,000, I am looking for when the y value of my curve is 100,000. So what if I draw another line on my graph right here, and this is just y equals 100,000. Then what I would be looking for is I'd be looking for this ordered pair right here. And I just want to know what is the x value where those two lines cross each other. Because this ordered pair, something 100,000 is the answer to the question. And of course, I know I can use my graphing calculator to do this. I can just plug the two functions in and calculate the intersection. So I'm going to grab my graphing calculator, and I go back to y equals, clear out what I had there. I'm going to go to my y1, and I am going to type in my function, which is 500 times 4 caret x power, right? 500 times 4 to the x. And then my second equation is going to be 100,000. Make sure you have enough zeros there. You should have 5 zeros for 100,000. And I am just going to calculate the intersection. Well, in order to do that, I have to make sure that I see the intersection in my viewing window. So I know that my y values have to go up to at least 100,000. I'm not sure where this happens along the x-axis. However, I know that 32,000 happens when x is 3. So I know that because I found that after 3 hours, right? So I know that it's probably going to have to be, I would say, an x value less than 10. I don't know how big yet, but an x value less than 10. So for my window, I am going to put my x minimum at 0. And I'm going to put my x maximum at 10. I'll leave my x scale at 1. My y minimum, all this action is happening above the x-axis, so I'll just put a y minimum of 0 in. And I will put a y maximum in of, and since I know that I'm looking for the intersection when y is 100,000, how about if I put 110,000? And I'm definitely going to turn that y scale off because otherwise it's going to look crazy. And then I'm going to go ahead and graph it. Ooh, okay. So you can see where the two lines cross, and it looks like it's somewhere between x equals 3 and x equals 4, right here, right here. So let's have the calculator calculate that intersection point for us. Second level, calculate number 5. And we do the first curve, second curve. Now, the cursor, we can't see right now. It's too far out. I was going the wrong way. Sorry about that. We know what's happening between x equals 3 and x equals 4. So if you're looking at those x values at the bottom of the screen, oh, there it is. I knew I was getting close. Okay. I just like to see it, my cursor, when it's asking me first curve, second curve. All right, so first curve, yes. Blue curve. Second curve, yes. Red curve. Please make a guess. And there it is. Our intersection is 3.822, and y is 100,000. So let's go back to our notes, and let's mark that down. This is going to be 3.822 is how long it should take. Now, we should be able to produce this same answer using algebra. So if I go back and I say, well, how long for my population to equal 100,000, that's my final question that I want to answer. So I want my final population to be 100,000. So I take my model, my P of t equals 500 times 4 to the t. And 100,000 goes over here. Because I want to know how long it takes to make that happen. So now the first thing that I would do would be to divide by 500. This is great algebra review here if you haven't done this in a while. And 100,000 divided by 500 is 200. Cross out some zeros if you need to. And then I have 200 equals 4 to the t. Now, some of you may be tempted to just divide by 4 and call it good, but no. That t is in the exponent, right? If you are trying to solve for a variable that is stuck up in an exponent, you need to change to log form. So if you were to change this to log form, then it would be t is going to be equal to log base 4 of 200, okay, which my calculator doesn't do log base 4. Remember, my calculator does log base 10, log base e. Your calculator probably does the same. But we have a little get around for this. It's called the change of base formula. I refer to that as the COB. So on your calculator, you just type in t equals, or well, you don't type t equals, but you do log of 200 in the numerator divided by, make sure you close your parenthesis, log of 4. And you hit enter, and you get that the time it takes to reach a population of 100,000 is 3.82 hours, which is the same answer that we got using our graphing calculator. Okay, so right here and right here, just a little note, same solution found graphically and algebraically. And you should be able to do this both ways.